Welcome to Section 7, Performance Optimization and Intro to Algorithms. In the previous section, we looked at advanced debugging and error handling techniques. In this section, we're going to investigate several different performance optimizations that you can apply to your applications. We'll look at how you can take advantage of compiler optimizations, we'll see how you can measure performance, we'll see some programming tips that can yield immediate results, and then we'll end this section by building an awareness of algorithms. Now we move on to the first video of this section that deals with identifying performance bottlenecks with XCTest and Time Profiler. In this video, we'll learn how to analyze our application's performance and identify expensive operations with Time Profiler. We'll then learn how to measure the performance of our code using XCTest. Understanding the performance implications behind our coding decisions is a very important step to becoming a good programmer. In this video, we're going to investigate two different approaches for measuring the performance of our code. The first approach allows us to take a high-level look at our application using Instrument's Time Profiler. Like the allocations tool we used to profile memory issues in Section 3, Time Profiler allows us to attach and record a debugging session which helps us to gain insight into the resource-heavy portions of our code. After we spot a performance bottleneck, we can then inspect the issue more closely to isolate the problem. The second approach is often useful after isolating a problem with Time Profiler. XCTest allows us to take a closer look at the speed of our operations. This allows us to quickly A/B test our code and see which choice is better for performance. Let's begin by opening our Game of Life application in Xcode. If you've lost track of your copy, you can always download the starter files for this video here. Once your application is loaded, go ahead and build and run it. We'll then transfer our session over to Instruments. In the simulator, go ahead and navigate to the Most Iterations menu and let our object construction process compute. You can see it register here in our CPU usage lane. Let's stop our Instruments recording and take a look at this. We can filter our desired results by clicking and dragging in the lane over the captured measurements that we wish to isolate. If you have a trackpad, you can pinch to zoom in, or if you have a mouse, you can hold Option and use the wheel to zoom in and out. Hovering over the timeline will show you your CPU usage over time. Notice that this operation uses over 100% of the CPU. This is because Time Profiler sums up all concurrent activity and, if you recall in the last section, we moved some of our work onto our background thread. Notice in our call tree view that the most resource-heavy operation is on the background thread, while our main thread still has some headroom. This is exactly what we wanted. We can inspect these processes with more granularity by expanding nodes. I'll expand them until I see the actual method calls that are using the bulk of the CPU power. You can see here that appending our objects to an array is using quite a bit of CPU. Once we have found a point of interest, we can double-click on the item and Time Profiler will show us the code in question. Let's look at another view of our recorded measurement. In the top right, we have three switches, which are called strategies. The first one is the CPU data strategy. It shows the CPU usage by core. We can zoom in closely to view the activity on our cores. This is an excellent way to prove to yourself that our operations are indeed happening concurrently. If you see any activity overlap adjacent swim lanes, you have concurrency. The next strategy is the instrument data strategy, which gives us a high-level view of our overall CPU usage. And the last view is the thread data strategy, which gives us a detailed view of our thread usage. These blue symbols represent snapshots taken of our thread, which allows us to see the stack from that thread at each given timestamp. Let's go ahead and measure our game's performance. We'll rerun our application and transfer our session to Instruments once again. Once Time Profiler has taken over, we'll run our game. So we see the bulk of our operation is on the main thread, which makes sense considering that the game board is being rendered over and over again based on our computations. Let's follow this resource-heavy node down the stack. If we follow it long enough, we find our custom filter we wrote in Section 2. This might be a good opportunity to A/B test with XCTest. We can test our filter against Swift's filter to see if there's a performance difference. Let's navigate to the Game of Life's test folder and open the Game of Life test Swift file. While we can certainly use XCTest for unit testing, we can also use it to measure performance, as we'll be doing throughout this section. At the top of our test class, let's create a placeholder variable for our life class. We'll utilize the setup function to instantiate our life class before each test runs, and we'll set it to nil in our teardown function to ensure that each of our tests starts with a clean slate. Finally, we'll utilize measureBlock function and add the code we'd like to measure. In this test, we'll be measuring the evolve block that contains our custom filter. Before I run this test, I want to point out that we are not running our entire game. We're running our evolve loop one time on a fresh instance of our cells class. So these tests are going to be pretty fast. Now let's run our test by clicking the diamond next to our class in the gutter. And our test completes. Next, let's open our life class and change our filter implementation to Swift's. We'll go back to our test file and rerun our operation. Notice we get very similar times. But Swift's filter is slightly faster in this case. We're going to continue this discussion in the next video. In this video, we introduce two ways of measuring the performance of our code. In the next video, we'll look at different compiler optimization modes.